Good morning, everybody. It's a pleasure to see you again. And today we are going to try to wrap up the topic which we discussed last week, which deals essentially with the gradient methods and the optimization problems in machine learning. And as we said, the optimization problem is the problem which is really at the heart of every type of machine learning method. And to be able to optimize the gradients, to calculate them in an efficient way, and also in a reliable way, with not wasting too many CPU cycles. This is one of the central points in machine learning, because at the heart of every method, there is the need to calculate the gradients in the optimization problem. And typically we end up with a convex optimization problem. It doesn't sound, as we discussed last week, like the most exciting topic, but it's actually a central topic in machine learning. And you will see that next week, when we move over to neural networks, you will encounter the calculation of gradients again and again and again. So any deep learning method has at its heart an efficient calculation of gradients. And in particular, since we are using variants of Newton's method, as we discussed last week, what we are essentially doing is to perform a second order truncation in a Taylor expansion. That means that we have a truncation at the order of the second derivative. And with the second derivative, we then end up with a problem where we update the unknown parameters, iteration by iteration, by calculating the gradient. And in principle, we need to calculate the second derivative of the cost function. So we have the gradient of the cost function and the second derivative of the cost function. This second derivative is a quantity which we call the Hessian. And it's normally, since we have more than one feature always, it's normally a matrix. And the whole problem is that we don't want to invert this matrix. And that matrix is replaced by a parameter. So let me quickly remind you of what we discussed last week. So what I'm going to do now is to scroll down to the part which is the essential for this week. So you will see also that the slides are dated November 7th and 14th. We did not finish properly the optimization part. And this is the part we want to finalize now, because when we move on to neural networks and other types of deep learning methods, and also other machine learning methods like support vector machines or decision trees and ensemble methods, you're going to encounter again and again the need to calculate in a reliable way gradients. So as I said, it doesn't sound like the most exciting topic, but it's actually a central topic in all of machine learning. So let's just scroll down to the topics which we looked at last week. And we used the logistic regression as the way to motivate the calculation of gradients. And what we end up with when we now look at the optimization part and link this with logistic regression, which is just an entry point for the discussion of these gradient optimization methods. What we had then was a set of equations for the logistic regression case where we have a probability P. Later, the gradients will be different when we are looking at other types of cost functions. Then we have the derivative with respect to the parameters we want to optimize. And then we have the second derivative, which is normally called the Hessian matrix. When we do standard linear regression, this Hessian matrix is just the transpose of the design matrix times the design matrix. So there is no matrix W which contains the probabilities. Remember that when we did logistic regression, we replaced the function f with a probability, because then we can say that if the probability is smaller than 0.5, then we have, in case of two classes, we have an outcome which could be false or just 0 if you want to put in a numerical value. And then if it's larger than 0.5, then the output is true, or 1 if we want to put in a numerical value. Typically, the way this is done is by using a as we discussed last week, a Taylor expansion of the cost function around the optimal value, beta hat, and as a function of the previous iteration. And the way these equations are solved, if we then use Newton-Raphson's iterative method, is in terms of an iterative scheme. And for logistic regression, that means that we have to invert this matrix for every iteration. And typically, when you solve this iteratively, you would have something like 100 iterations. Between 50 and 100 is normally the kind of way you would do that. And then if you have now 100 parameters, it means that you will have to invert this matrix 10,000 times. So you have 100 parameters, and then you would do 100 iterations. And in every iteration, you calculate this matrix, as you can see here, in terms of the previous values. And same with the gradient. So this is the gradient, and this is the Hessian matrix, which we have to invert for every iteration. And that clearly becomes time consuming. And when we're moving to the neural networks and deep learning methods, what you will see then is that the number of parameters are going to be in the hundreds of thousands, or even in millions. We will have millions of parameters. And then clearly you don't want to invert a matrix, which is 100,000 times 100,000. And you don't invert that if you do 100 iterations, 100 times for 100,000 parameters. So that motivates the introduction of what we called a parameter, which we call the learning rate. And then we could play around with the different learning rates, because it's cheaper from a computational point of view to have an array of learning rates, which replace this matrix, which you see here, and then simply calculate these learning rates with different values, and then optimize and find the results which are most stable and which give the best, let's say, mean squared error or score as a function of a chosen learning rate. Now, what we are going to discuss today are actually ways by which we can adapt or find an adaptive way of replacing that learning rate, so that we mimic, in a certain sense, the calculation of this Hessian matrix. Now, there are methods which are called quasi-Newton methods, which try to circumvent the problem by calculating an approximate to the Hessian matrix, iteration by iteration. But in general, when we deal with machine learning, we want to calculate this in as few cycles as possible, and with as small computational complexity as possible. And then we need to find ways by which we can calculate this quantity here. So this is the basic aim today. And let me quickly remind you also of some of the calculations which we did last time. So we also discussed a method which is called the steepest descent. We are going to bring that up here again today. But the slides contain some basics about the steepest descent method, the properties of convex functions, etc., etc. So last week, where we essentially ended was to look at some specific applications of this gradient descent method, the plane gradient descent. And in that case, we just revisited a simple data set where we had the x's as a random value, and then the y's as a linear function in the x's. Sorry for the coughing here. I mean, I've got a small cold. And in the case which we had, we picked a set of data which contained now 100 entries x, and we wanted to fit a first order polynomial where we kept the intercept. And in that case, the cost function for ordinary least squares is given now by this function which you see here. And we calculated the gradient, which takes a pretty simple expressions. We could also calculate, if we wanted, the Hessian matrix, which is given by the second derivative. So this is nothing but what we normally call a Jacobian. And in this specific case, we could actually invert this matrix. And we discussed a simple program where we now have the x's. We could add some random noise if we wanted to. The thing which we discussed also last time is that there is a constraint on this parameter, the learning rate, which can be calculated using the eigenvalues of the Hessian matrix. So we actually calculated this Hessian matrix, and then with the Hessian matrix, we could then actually find that if we included the Hessian matrix, we needed essentially 1 or 2 iterations before we actually got the exact values. If we could bring that back, we can then define a learning rate, which in this case would be equal to 1 divided by the max eigenvalue of the Hessian matrix. And then we would simply replace this Hessian, the inverse of the Hessian matrix, with the learning rate eta. And when we then run the calculations, now I have to bring that up here because it seems that I had forgotten a parameter to comment out that one. When we did that, oops, it seems I was a little bit too fast here. Yeah, I made some modification where last time we just run with the Hessian matrix, and now we have to update again here. So sorry for this, I was a little bit too fast here. Because last time we replaced this with a matrix, and now it works. And you see that in this specific case, when we now had a learning rate and we had only 1 iterations, we end up with a value which is far away from the exact value. So then we have to increase the number of iterations here, and that becomes a parameter. And you see now in this case that we're getting closer and closer to the exact value. And if we increase the number of iterations, you will get this one closer and closer. So if I just put an exaggerated number of iterations to 1,000, then I'm getting exactly the same values, which I get by standard matrix inversion in ordinary least squares. And in this case, I'm using the largest eigenvalue as the learning rate. And we saw last time that if I now were to increase the value of the learning rate, so suppose I put that one equal to 1. If I do that, I end up in a situation where the results are not converged at all. If I make the learning rate very, very small, what we end up with then, if I just decrease the number of iterations, is also a situation where you see now that we haven't reached the ideal value. So when I make the learning rate very, very small, then I need to increase the number of iterations to a very large number. So if I put that to 10,000, you see now that I'm gradually approaching the correct values. But with such a small learning rate, I will still need many iterations to actually reach the final exact value. So the learning rate is one of the central points which we are going to discuss today, and how to actually improve this type of calculations where we have an adaptive learning rate, which then changes from iteration to iteration. So let's quickly just remind ourselves of some of the pros and cons of a standard gradient method before we move into the modifications which are needed in order to get a reliable calculation of the learning rate without at the same time having to calculate this Hessian matrix. So the gradient descent to find the local minimum of function. So the method is deterministic, and if it converges to a local or global minimum. But since we are dealing with pretty rough landscapes in many cases, we may not know whether we have a global minimum or local minimum. So the method it's easy to implement, but it can lead to poor performance. And as you saw, the learning rate and the gradient descent methods, they are intimately linked. And the gradient descent is very sensitive to the initial conditions. And as you will see today, the way we can try to modify this may help in the convergence and in us getting reliable results. The gradients themselves are computationally expensive to calculate for large data sets. In the calculations which you saw above here, we're actually calculating the gradient. So if you look at the calculations here, this is an example for ridge regression. We are performing now a matrix multiplication here, and then we multiply that with a vector, and then we have a matrix multiplied with a vector. And if we run over the whole data set, this becomes really time consuming. And if you have something like hundreds of thousands of data points, clearly you're performing matrix multiplications with large data sets. That means that the gradients, as you can see here, they are computationally expensive to calculate for large data sets. That leads to what we normally call a stochastic gradient descent, where you calculate the gradients for smaller sets of data, and then you loop over all the data set, but at each step, you just select, let's say you have 10,000 points, you select just 100 points. So you split your data set in so-called 100 batches, and then you perform the matrix and matrix vector multiplication for just 100 data points. And that is, from a computational point of view, that is computationally less expensive than calculating the gradient for all the data points. And then, as you've seen in these simple calculations, the gradient descent is very sensitive to choices of learning rates. And the other thing is that when you do a gradient descent, the way we have presented it, which is just a simple approximations to Newton's method, what we end up with is actually that all the parameters change uniformly. So if you have gradients which vary a lot in one direction and less in another direction, when we multiply it with the same learning rate, then the gradients change actually in the same way. So just the a constant learning rate multiplied with different gradients. So one of the ways to do this is actually to include what's called a gradient descent with momentum. And this is one of the topics which we are going to discuss today first. So let's bring back the whiteboard before we just move on here and look at examples. So I'm just going to change to the whiteboard. And then we're going to take a look at the kind of strategies which we're going to implement here. And this is, how to say, this is really something which is at the heart of all of machine learning here. So we have a basic method. So let's repeat this. So we have some parameters which we're going to update in an iterative way. So beta can be a vector or it can be a scalar. Normally this is going to be a vector. It's going to be a vector of all the unknown parameters we have. And typically we would have, when we deal with neural networks, when we look at the weights of a neural network, these are going to be parameters in the orders of hundreds of thousands of millions. So that means that we have a vector of a pretty large length. And then we have to multiply, or we have to subtract the gradient. But then we would typically have a learning rate, eta here, gamma here. And this is multiplied with a gradient, which I wrote last time as a g of n. And g is actually calculated at a value for the for the parameter beta at iteration n. And then we keep updating. This is the basic equation we're going to meet again and again in all of machine learning. And then this parameter here, the learning rate, is a parameter we can just keep fixed. So let's see the kind of recipes which we can do now. So one is the update of the learning rate of gamma of n. So there are several ways of doing that. One is the simplest possible one, which leads to standard gradient descent, and that is just to keep it fixed. So we keep the same value for every iteration. We would typically then just set up an array of learning rates. Let's say the learning rates goes from 10 to the minus 5 to 10 to the minus 1. And then we simply calculate for a grid of learning rates. And then we pick the values of the, let's say, the mean squared error, which is the smallest one. And then we say that for that specific learning rate, we have the optimal mean squared error. So one approach is just to keep fixed for all iterations n. That's the most brute force way we can think of. Another way of doing this is to have a kind of way to change the learning rate. So one of the pretty simple way is actually to have a linear change. And the simplest way to do that is simply to have some kind of parameter. So we could have a learning rate gamma of k, iteration k, which is equal to 1 minus some alpha. And then we have a gamma 0, which will be the first learning rate. So we feed into the algorithm an initial learning rate. And then we have some parameter plus some alpha plus some gamma of tau, which is a constant here. And in that specific case, this alpha could now be given by number of iterations divided by a parameter tau here. So tau is a parameter which we need to fix. And this gamma of tau is also a parameter, and that's normally fixed to something like a hundredth of gamma 0. So how we would typically have to select this parameter gamma 0. And then you would typically say that gamma 0 could then be chosen to be in an array of 10 to the minus 5, 10 to the minus 4. This is just an example of a typical choice of parameters gamma 0 to something like 10 to the minus 1. So you would have an array of such parameters, and then you would have a kind of adaptive way of doing that. There are many ways of doing this. So you could have another one. We have a gamma of k, and this is one of the examples which is encoded in the examples which we have below. So you would have 1 plus k, which is a parameter, and then we have this parameter gamma of tau. This is another way of doing that. So these are all called schedulers, and it's a very much ad hoc way of doing that, and you will find many of these ways. So you have an exponential decay. And as you see here, there is no insight about the way we relate this gamma of k to the gradients and the second derivatives. So the exponential one would be a gamma of k, which is now given by this gamma 0, which is the initial value. And this is simply multiplied with an exponential, where we have the number of iterations, and then again multiplied with this parameter gamma tau. So that means that you're introducing a new set of parameters, gamma 0 and gamma tau here. Then there are several other algorithms which are more advanced, and these algorithms, they try to include information about the gradients and in a way to approximate the Hessian matrix. So what you would find then is something like the methods which try to approximations of the Hessian matrix, which is the second derivative of the cost function. And here we are going to meet methods like ADA-GRAD. And then we have a root mean square propagation. So we're going to discuss these methods today. And then we have another method which is widely popular, which is just called ADAM. So these are ways by which we try to calculate the learning rate by introducing some information about the Hessian matrix and the gradients. So this is going to contain information on gradients. So this is one set of topics which we're going to cover today. So the update of the learning rate. Then there is another topic which deals with efficient calculations of gradients. And the one of the first topics which we're going to encounter is called momentum-based gradient. And this is something you can implement irrespective of method you're dealing with. So if you look at the way we treat the learning rates here, this is a method which you can accompany with any of these ways of updating the learning rate in an adaptive way, or whether you do this more kind of what I normally like to call ad hoc brute force methods, where we simply have either linear change or just keep it fixed, or we can have an exponential decay of the learning rate. Or we can use the more advanced methods which have information about the gradients. But the momentum-based gradient descent is something which we can do irrespective of the way we treat the learning rate. So I want you just to keep this in mind. So we have ways of adaptively change the learning rate, but then we also have efficient calculations of the gradients, so which is the other major topic. And there are two central methods which you will encounter. So the second one is actually something which is called the stochastic gradient descent. And we are going to spend some time on both of these methods today. Let's take a look first at the momentum-based gradient descent, because this is a method which essentially keeps track of the information from the previous iterations. And you're going to see that this is something which actually can speed up the convergence as a function of number of iterations. And we are going to see that as soon as we've gone through the mathematics of the standard momentum gradient descent here. So momentum gradient descent is actually something which is inspired by the solution of Newton's equation. But you could also think of this as a method which many people simply derive using a parameter which you multiply with the information from the previous gradient. And some people would like to call this momentum-based gradients as memory-based gradients. So you keep track of the information from the iteration before beta of n. So let's take a look at the momentum-based gradient descent. So what you're doing now is that you're weighting the new iteration with information from the iteration before. And by doing that, what you obtain is a softening of gradients which may vary a lot from one iteration to the next one. So if you have large changes in the gradients, by keeping track of the information from a previous step and weighting that with a specific parameter, then you can soften wild variations in gradients, which may happen if you are in a region where the gradient varies a lot. So let's see why this is called a momentum-based gradient descent. Now think of you having a equation which is Newton's equation, and this is the reason why it's called momentum-based. So if we start with Newton's equation of motion with a friction term or drag term, then we just limit ourselves to a one-dimensional problem. So we would have the acceleration, which is the first term, and then we can have a friction term, which is now given by a constant times the velocity. So this is normally called a friction term, friction or drag coefficient, this term which you see here. And then this is equal to the force which is applied to the system. So we would have an f of x, and we know that this is given by the gradient of the potential which the particle moves in. So if we have a potential, we know that the force is given by the gradient, the negative gradient of the potential. And this is something which now brings us back to the information about the gradient. So this is now the closest we get to the similarity between a gradient and the Newton's equation here. So if we now look at the second derivative, the way we would typically calculate this is by approximating it with a 3-point formula where we look at the value at the center. So we would have an x of t plus delta t. So we have a step size in time. This is given by -2 of x calculated at the time step t plus x of t minus delta t. So this is normally called a centered equation where we have 3 points, and then we can approximate the second derivative with this equation here, where we have calculated the values of the variable x at 3 points. And this is divided by delta t squared. Similarly, we are going to use the standard Euler formula for the first derivative. So this would now be approximated with x of t plus a delta t minus x of t divided by delta t. So these are typical approximations which you will find in the literature. So this means that what you get then, when you plug this into Newton's equation of motion in this specific case, is that we have a formula which says that we have m times x of t plus delta t. So I'm just bringing this up to try to motivate why people call this a momentum-based way of dealing with it. And then we have a delta t squared, and we have a plus a mu, this friction parameter of x of t plus delta t minus delta t divided by delta t, and this is equal to minus the gradient, the first derivative of the potential. Then we are going to define 2 new parameters. So I define a delta x of t plus delta t here, which is simply given by x of t plus delta t minus x of t. And then I define delta x of t, which is now given in terms of the previous value of minus x of t minus delta t. So if you now look at the equations which we have, we can now rewrite the equation for the second derivative, which we have here. So we have an x plus a delta t minus x of t. We take one of them, and then we can rewrite that in terms of this equation. And then we take the other x of t and the x of t minus delta t, and then we can rewrite that in terms of delta x of t. This equation here is also an equation which we can rewrite in terms of this term here. So if we just replace many of the terms with delta x of t, and then isolate that one on the right-hand side, so we would have a delta x of t plus delta t, which is then given by minus delta t squared. So I'm just reorganizing here, and then we have m plus mu times delta t multiplied with the gradient of the potential plus a term m with m plus mu of delta t times delta x of t here. And then I introduce a new parameter which I call for delta, and that's given by m divided by m plus mu times delta t. And then I can rewrite this equation in a simpler way, and then I can simply set up. So I'm going to introduce a new parameter which I also call gamma, which is now delta t squared divided by m plus mu times delta t. And that means that I can rewrite my equations in terms of a delta x of t plus delta t, which is equal to minus gamma. So this reminds us very much of the learning rate. And then we have the gradient plus a delta times delta x of t. So this parameter delta, which you have here, can be thought of as a memory parameter. And you see that this parameter depends on the value from the previous iterations, right? So you remember that delta x of t is given by x of t minus x of t minus delta t. So what we have here, the way we have rewritten it, is an iterative scheme where we have the new update given by the gradient, but instead of having only the new one, or rather the previous value, we also keep information about the value at the previous stage. So let me just remind you quickly of what we are doing. So we would typically have a parameter beta of n plus 1, which is given by the parameter beta of n minus a learning rate times the gradient of the cost function, which is a delta of C of beta of N. So if you look at the similarities now, what you have is a clear similarity here with this equation, the way we have defined things. But now you see that the equation which you have here is not given by just this one, because then we would simply have had this term, but it contains now information about the previous iteration, this x of t minus delta t. So what we are doing in a way is that we are modulating the presence of the previous result with a parameter delta. And this parameter delta becomes a new hyperparameter in the theory. So what you would see typically then is something like this when you're seeing these equations. So you would have a delta beta of I plus 1. So let's just put that one in, which is then given by a beta of I plus 1 minus beta of I. And we will simply set up a new equation now, which is beta of I plus 1, which is equal to beta of I, the previous iteration, minus a learning rate, gamma of I, of delta of the cost function, calculated at beta of I, plus a parameter delta, which now functions as a kind of memory parameter. So we would have a beta of I minus this beta of I plus 1. So the this parameter delta, if you now look at it, the way we have defined it, this parameter delta here, if we now let this mu parameter here go to infinity, then this delta is just m divided by mu of delta t. So you can think of delta as a kind of memory parameter, and it scales the equations and multiplies that with the previous value. The way this is normally rewritten in actual calculations is as follows. So we would define a parameter which people normally call the velocity. And this is given by a delta, this parameter which we had. And then we would have a v of I minus this v of I minus 1 minus gamma multiplied with so this is v of I there, and then we have a v of I multiplied with the gamma, and this is calculated for a gradient at the value v of I. And these parameters which we want to find, beta at I plus 1, is now given by the parameter beta at iteration I plus this so-called velocity or pseudo velocity. And typically this parameter delta which we have is chosen to lie between 0 and 1. And this becomes a hyperparameter which we have to play around with. This normally, by having this type of information, can actually speed up the convergence of a gradient descent method. Now, this momentum-based method is something you can implement in every single method. So when you do a stochastic gradient descent, if we go back now and look at the two main issues, one is the efficient calculation of gradients. So we can implement this momentum-based gradient descent with stochastic gradient descent, but we can also implement it together with all these methods. We can have adaptive gradients, we can have root mean square propagation. Now what Adam is doing is actually to bring in momentum. So the M in Adam stands for momentum-based. It's an adaptive gradient or adaptive learning rate with momentum. So Adam incorporates momentum-based gradients, whereas AdaGrad and root mean square propagation, especially AdaGrad, does not have the momentum-based approach, but you can include that one in AdaGrad. So what I'm going to do now is just to switch back to the Jupyter notebook And we are going to look at some simple examples on how we can include this momentum-based approach. So the function which you're going to see now is a simple function where we have a function which is the function we are producing now, has x squared, and then clearly the derivative is just x times 2. And in this case, I'm now doing a standard gradient descent, and I'm calculating this for a given step size, as you can see here. And the step size is a parameter I've defined to be 0.1, and I do this for 30 iterations. And what I'm doing now is simply to write down the gradients as they're calculated iteration by iteration. So ideally, we want to drive the gradients to 0. And you see now that after something like 24 iterations or 25 iterations, we are getting close to a gradient, at least for 5 leading digits, which is close to 0. And you would see when we plot it, you can now see that we start here with a guess, and we are gradually just in steps of 0.1. We are just going slowly down to the final point where the roots of the functions are 0. And then we have a gradient which is 0. Now you can, if you look at the gradient descent with momentum, so this is just plain gradient descent with momentum. And here you can see now that what we've done is that to set the new change equal to the step size times the gradient. So we need to calculate the gradient first, as you can see here. And then we have the momentum times this change. And so we have put the change equal to 0 in the first iteration. And now we are looping over the number of iterations. And then the solution, as we put up in the on the whiteboard, is given by the solution minus the new change. Change now is new change. And then we simply append the solutions here. And then when you look at the results, so in this case, I put this parameter to 0.3. And you can see now that after 12 iterations, instead of 25, 26, our gradients are basically equal to 0. And that means that we can really speed up the calculations of gradients. So this is one way which we normally would do the calculations, by including this memory-based information. And then we can update iteratively the gradient as we did before. So momentum-based gradients is something which is normally implemented. You will find this in all kinds of iterative schemes. So if some of you are going to do mean field calculations in quantum mechanics, like Hartree-Fock theory or density functional theory, you will see that there is always a parameter which you include in order to keep information about the previous gradient. So you don't need to bring in these derivations using Newton's equation, as I showed you, but that's just a way to, how to say, get a kind of understanding why the method is called momentum-based. So many people just include an ad hoc information about the previous iteration. But you can reframe this or rephrase it in a nicer way by linking this up to the solution of an equation of motion like Newton's equation. And this is why these are normally called momentum-based methods. Or if you just want to keep a simpler name, memory-based methods. So the next topic, which we are going to look at now after the break, are actually so-called stochastic gradient descent methods. So in stochastic gradient descent, what we are doing then is to take the calculation of the gradients, and instead of evaluating the gradient for all the points, we are now going to stochastically find a starting point, and then from this starting point, we calculate the gradient as a function of just a few selected points. And then we repeat this till we have gone through the whole data set. And then you can repeat this again and again, a given number of times. So what we're actually calculating is an expectation value of the gradient by doing this stochastic gradient descent. And this is something which we are going to detail a little bit after the break. And then when we're done with that, we are going to include these other methods like ADA grad and RMS prop and ADA, so that you would have a complete set of methods, which we then are going to include in the first project. So the first project is going to be available by the end of this week. And that is going to include studies of linear regression methods together with and without the implementation of a gradient descent method. Okay, so I propose that we take a small break and then we dive into stochastic gradient descent and the modifications of the calculations of the learning rate, where we bake in gradually more and more information about the gradients in the calculations of the Hessian matrix. Before we move on to stochastic gradient descent, I just wanted to give a small update on the momentum gradient descent. And in the handwritten notes, which I set up before the break, I actually had misspelled it. This parameter v of I here is actually given in terms of the parameter beta, which is the one we want to optimize for the iteration I, minus the result for the iteration beta of I minus 1. And the algorithm for this specific case, when we want to set up the momentum-based gradient descent, goes as follows. So the first thing is that we require a learning rate. So we need an initial value for the learning rate. And we can decide then whether we want to have this learning rate to be scaled as a function of iterations, or whether we want to just keep it fixed. But we need a learning rate as an initial value. And then we need also the momentum parameter, which we called for delta. And then we require, in addition to that, in order to initialize the algorithm, we need an initial value for the unknown parameter beta. So these could be random values. And this parameter, which we called v. And then we have the algorithm, which simply says that v of I is equal to this parameter delta of beta of I plus I of I minus beta of I minus 1. And this is then we add to this or subtract the gradient, which is calculated at a parameter beta of I. And then we update in iteration I plus 1, we update the new value. So we have this one given by beta of I plus v of I. So then when we set up the algorithm, we do this while we have a stopping criterion till we have reached that one. Not met. So this is simply a while loop. The first thing we do now is to compute the gradient. We can put gradients because this is normally a multivariable quantity. Then we have to evaluate this update. And we normally call this a velocity, v for velocity. V update. So we would calculate this v of I as written above, where we keep the information about the previous stage. And this is now given in terms of the gradients of g of beta of I, which we get from this quantity here. We compute the gradients first. And then we apply the update. And we keep iterating till we have reached the convergence criterion. So this is beta of I plus 1 is equal to beta of I plus v of I. And this is end while. So this will be the algorithm for the momentum gradient descent, and where we haven't looked at ways we calculate the gradients. So what we're going to do now is to look at stochastic gradient descent as a way to calculate in an efficient way the gradients. So stochastic gradient descent for the calculations of the gradients. And then this normally is called stochastic gradient descent with momentum. So stochastic gradient descent for the calculation of G, the gradient here. So what we are going to do now is simply to look at the equations or the algorithm which we have here. And then instead of calculating the whole gradient, we are going to look at the stochastic calculation of the gradient. Let me try to give you a kind of motivation for why we calculate the gradient stochastically. So there are many reasons for why we do that. So the main reason is simply that this is something which introduces less CPU cycles when we calculate the gradient compared to us performing, for instance, for ordinary least squares, a full matrix and matrix vector multiplications. So let's now look at the given function f of x as a function of x. So suppose the landscape looks something like this. So typically the point which you see here, that would be a saddle point. This is a point where the gradient would be 0. This is another point where the gradient would be 0. Same here and same here. Now this point here is the one which we ideally want to reach and which we would call a global minimum in this case. So this is the global minimum. Whereas the other ones, minimum, this would be a local minimum. And same with this one. Whereas this one will be a delicate point, which is normally called a saddle point. And they can be quite vicious, actually, because you can be stuck in a saddle point for some time before actually the algorithm keeps moving. Now, the problem now is that if we start the calculation here, for instance, then after some gradient stepping, we may actually reach this point, and then our algorithm will stop because we have reached the convergence criterion, which states that if the gradient is 0 or the parameters don't change more than a specific value, then we would then be happy with the results which we have here. So if we start our iterations at a random value here, we may actually end up in the wrong point. Now, the thing with the stochastic gradient descent, what happens then is that we, in a data set, suppose we have a data set X, which now includes X0, X1, up to some Xn minus 1. What we're going to do now is to calculate the gradient in batches, in smaller, for smaller regions. So we would typically then calculate the gradient by positioning ourselves randomly at a position here, for instance. And then we would then calculate the gradient for a given number of points. So it wouldn't be the full set of points. So that means that we could calculate the gradient down here. That would be one contribution to the gradient. Next time we could place ourselves randomly here. And then we would calculate the gradient again for a given number of points. And then we would repeat this operation till we have reached the total number of points. So what is common now is to split this data set, which we have, split n, the total number of points, n, number of n of x values, in so-called batches. So we could then split this in batches with a given number of data points, with a given number of data points. And this number of data points could be something like a little m, let's call this little m here. And then we would have a total of m batches. Just to give you an example, if we now have n equal to 100 points, then we could say that we have m equal to, let's say, 10. Then in each so-called mini batch, these are normally called mini batches of data, we have 10 points. And then we would evaluate the gradient for these 10 points. And then we repeat till we have traversed all the possible batches. That would define one epoch. So we have an evaluation of the gradient. And then we repeat this by placing ourselves randomly in different regions. And the hope then is not only to be able to reduce the number of cycles needed to calculate the gradient, but also to be able to capture a possible global minimum by placing yourself randomly in many, many different places. And just to repeat this again and again and again. So let me show you what a typical implementation of the stochastic gradient descent. So let's go back to the Jupyter notebook and take a short look at the code examples which we have here. So in stochastic gradient descent, and sometimes people call the stochastic gradient descent, you have to be a little bit careful. Sometimes just stochastic gradient descent means that we run through all the data points, but it's normal nowadays to actually call stochastic gradient descent, that means stochastic gradient descent with these mini batches. And these batches are normally set up in as powers of 2, since this often can lead to a better vectorization of the codes. So the stochastic gradient descent, if you look at this simple example which we have here, so we would have the number of mini batches run from k equal to 1 up to the number of data points divided by the number of batches which we have decided upon. So if you have 10 data points, as in this case here, and you have chosen 5 mini batches, then each of them would contain points x1, x2, etc. Normally, these points are chosen randomly. And I will show you below how you can actually implement this. So the approach then is actually to replace the sum over all the points by a calculation of all these mini batches. And then you simply collect the gradients as a function of these mini batches. So let's take a look at a simple code down here, which does it for us. This code actually contains a scheduler for introducing an adaptive learning rate. So this is a cheaper way of calculating the learning rate. And in this case, we actually scale the learning rate with an initial value. And then this is updated for iteration by iteration, where this t here is now something which corresponds to the number of iterations multiplied with the number of epochs. And epochs is if you look at the loop which we have now, you would have an inner loop where we pick randomly a starting point for the calculation of the gradient, and then we evaluate the gradient for just the number of points which we have decided to be in a mini batch. And this now runs over the epochs. So the number of epochs, as you can see here, becomes a new parameter where you repeat again and again the calculation of the gradients. And then you need to define the size of each mini batch and then the number of mini batches as discussed here. So here we have a simple example again. It's the same data set which we looked at in the previous case. We have a random value for x given by a uniform distribution, where x is multiplied with 2, so we have random numbers between 0 and 2. And then I calculate y, which is just a linear function, and I've took away the noise here. Then I perform the standard linear regression calculation, where I invert the matrix and I get the parameters. And now I'm setting up a standard gradient descent here with a learning rate, which is motivated by the eigenvalues of the Hessian matrix. And then I have my stochastic gradient descent here, where I have a scheduler for the learning rate. So these are more ad hoc formula, and you will find many ones. You can have a linear one, you can have an exponential one, or you can just keep the fixed learning rate. And then you run over the number of epochs, which I defined to 5, and then you have these parameters for the scheduler. So this is a very much ad hoc formula. And now you can see that what I'm doing, I'm picking up a data set by placing myself randomly in the array of the data points. And then I find the xi's and the y of I for that specific mini batch. And then I calculate the gradient. But now the gradient has to be divided by the number of points in the mini batch. Whereas previously we had a division by the whole number of points. So the calculation of the matrix x transpose times x here is faster than running through the whole data set. And then I update, so I have a kind of cheap way of updating the learning rate. And the next thing I do then is actually to calculate my update of the parameters theta, or beta as we call them, multiplied with the learning rate here, which is being changed gradually. And this is a gradient, which is then calculated for every single mini batch. By doing this, if we run the code, you will see that we are not getting exactly the exact values, because we are now calculating this in a stochastic way randomly. And you will see now that when we do the standard inversion and the standard gradient descent, where we allow for many iterations, we are getting the exact values. Whereas my stochastic gradient descent is getting pretty close, but you won't get exactly at the value which you're looking after. But you see, it still is doing a decent job. If I add some noise here, this may change a lot, because then the fitting becomes more difficult, because we have many outliers. And simply fitting a straight line may not be the exact result. So, but you will see now that my own inversion and my own stochastic gradient descent by using the Hessian matrix gives me very good results, basically the same. But the stochastic gradient descent is also not so bad. So it's pretty close to the exact value which you see here. So there's something I want you to take a look at if you have time. There's actually a discussion here, because what you see now in this specific selection, this is a random choice with replacement. So that means that when I get back, I can actually pick the same starting point. So that means that I will calculate the same gradient again. And there is actually a debate whether you should use replacement or not. So if you want to look up that discussion in the calculation of the gradients, there is a very nice discussion in the link here. So actually calculating these gradients, as you see, it becomes quickly, like in the example here, a case for different interesting explorations. And one of the things which you saw here is also the way we pick the points randomly, but also the scheduler for the learning rate. And the scheduler for the learning rate is something which we are going to look at now in terms of a modified algorithm, which is called adaptive gradients, ADA-grad. And then we are going to look at root mean square propagation, and then adaptive gradient with momentum. So all of these methods can include momentum or not, but then we can also look at the way we update the learning rate. So here we have this very cheap recipe for updating the learning rate. So what I'm going to do now, before we set up the algorithms for adaptive gradient, ADA-grad, or root mean square propagation, just as examples, I wanted to remind you quickly about a method which is called the standard steepest descent, because that gives us a kind of way to intuitively say something about what the learning rate could be and how we could update it. So let's take a look at the steepest descent, the mathematics of steepest descent, which is one of the simplest possible methods, but that's also going to give us a guide on how we could approximate this Hessian matrix and what these methods like ADA-grad, root mean square propagation, and so on are actually doing. So let's take a look at the whiteboard again. So what we want to do now is the following. So if we scroll back a little bit to what we had before the break, I just need to unlock my whiteboard. So before the break, we set up the overarching issues. So one is the efficient calculations of gradients. So we discussed momentum-based gradients. So this is a general recipe which you can implement irrespective of ways you update the learning rate. Then the stochastic gradient descent is an efficient way of calculating the gradients. And this is normally what is done when you have huge data sets. But then we have these ways of updating the learning rate. So let's take a look at this part now, because this is the one which leads us to the interesting methods like ADA-grad, the root mean square propagation, and ADAM. So let's go back and have as a small mathematical intermezzo a method which is called steepest descent. So steepest descent is a method which is an intermediate step between the plain brute force gradient descent and the more advanced sophisticated methods like conjugate gradient descent, which are the typical methods you would use if you can deal with the calculation of the Hessian matrix. So typically what we have is a problem of this following type here. So the x's are now matrix vectors, and this problem which we have seen when we approximated in the previous week, the cost function, is that we could rewrite this in terms of a second derivative, which was a Hessian matrix, and this is this matrix A minus x transpose times a vector B. B is known. And when I then calculate the derivative of df of x of d of x equal to 0, that gives us A times x, A is a matrix, minus B, and that leads to a standard linear algebra problem, AX equal to B. Essentially, this is our standard Newton method when A is the matrix, which is defined by the Hessian matrix, the second derivative of the cost function, and X are the parameters beta. So this function B plays the role of the gradient. So B here is a gradient. So the typical way you can solve this equation is obviously if you can invert the matrix, you would find that X, the unknown, is A minus inverse times B. B is known and A is known. So in our case, A is the Hessian matrix, so this quantity here, and B is actually the gradient, and the gradient which is calculated at the previous value of beta of n. And the Hessian matrix is also calculated at the previous value. But if you can invert the problem, then you have solved the problem. So what I'm setting up here is actually nothing but the cost function evaluated with a Taylor expansion, where we have truncated the Taylor expansion at the level of the second derivative. And this is what we did last week when we analyzed the cost function. And we can now rephrase this in this kind of more general way. So the standard way to solve this type of equations is to define, and this leads to the steepest descent method, which is a kind of a stepping stone towards the full gradient descent, is to define a residual R, which is now given by B minus A times X. And we are going to solve these equations iteratively. So we have the solution. So we don't want to invert the matrix. We have the solution when this residual R is equal to 0. So typically with them, what we would have is to start with a guess with x0. So we start with a guess, which we will call x0. And that gives us a residual R0, which is simply minus A times x0 plus B. And B is a quantity which is known. X0 is something we could put to 0, or we could just give it some random values. but so we have an initial guess. Now, there is a very important statement. If this matrix A is positive definite, then this process will converge to the exact value, x, irrespective of starting point. That's a pretty strong statement. But that applies only if the matrix is positive definite. The Hessian matrix, which we are going to deal with, like in logistic regression or linear regression, is positive definite. And that means that this process will converge. When we come to neural networks, we have no idea whether the matrix will be positive definite or not. So in that case, we may not have a clear convex or concave optimization problem. Okay, so the way we will do now is that in general, we have the following. When we have performed a given number of iterations, we would have a residual R of k plus 1, which is equal to b minus a of x k plus 1 here. And that means that we would have an xk plus 1 in general, which is given by xk plus some parameter alpha of k multiplied with r of k. So this equation which you see here, the first one just follows from what we have. And here we have made an assumption. We're also going to make an assumption that these residuals and the x's are orthogonal to each other. So if we now rewrite, so this equation here is an assumption. We will now simply say that there is a parameter alpha of k multiplied with the residual, which relates the new value with the previous value. Next, what we have is that we can obviously rewrite this rk plus 1. We can rewrite that as b minus, with this assumption we made now, of x of k plus alpha times r of k. And this is something which we can rewrite as b minus a of x of k. So we know that this is the same as the definition r of k, plus is actually minus, and this should be an alpha of k multiplied with r of k. So what we have then is the following. So we have that r of k plus 1, the residual in the next step, is given by the residual in the previous step, multiplied with alpha k of a times, so this, I actually forgot one thing here, sorry for that. So we have a times r of k, I forgot the a here. So what we have then is a multiplied with r of k, and what we want is obviously the following. So we want this r of k plus 1 equal to 0. So what we're going to do next is actually to multiply with the r of k transpose on both sides. And we're also going to assume that r of k plus 1 transpose multiplied with r of k is equal to 0. So we're assuming now that the solutions are orthogonal to each other. This is the residuals. If I then multiply with rk transpose on both sides of this equation, which you see here, what we get then is r of k transpose times r of k plus 1 is equal to r of k transpose times r of k minus alpha. Alpha is just a constant, and then I have rk transpose multiplied with a of rk. And then what we can assume now, if this process has converged, then clearly this should be 0. We can also assume that these are orthogonal. We don't need to assume that, but we could assume now that this has converged when rk plus 1 is equal to 0. So we are going to assume now that this side here is equal to 0. And this could be achieved by either have orthogonal solutions to each other for every iteration, or assuming that we have reached the converged result where rk plus 1 is equal to 0. So that means that when we now reshuffle things, we can now define this parameter alpha of k equal to r of k transpose rk divided by rk transpose times a of R of k. So if we can define these parameters, and we can do that when we have a guess, because when we have a guess, we know that the values of this R of k are given by this term here. We know the x of k, we know a, and we know this parameter b, or this vector b, and that means that we can calculate R of k. So we have a value for it, and that means I have a scalar here, and I have a scalar here, but clearly, as you can see, it requires us being able to calculate the Hessian matrix. And remember now that the Hessian matrix is the second derivative of the cost function. So this is an expensive quantity to calculate. And we may not have analytical expressions for the derivatives. So you see all the problems which we face when we are dealing with many of these methods. So the calculation of this parameter, alpha k, is a parameter which we are going to interpret as the learning rate, because now this is inserted back into xk plus 1 equal to xk plus alpha k times R of k. Now, in our case, what we had originally was a function df dx, which we found to be equal to ax minus b. And this is the same as minus this gradient g of x, as we have defined it. So that means that our x of k plus 1 is actually x of k minus this alpha of k multiplied with this g of x. So this is the interpretation we are going to make when we, because this is the same as minus b, minus b so this is a minus, and then we have b minus a times x. And this is a quantity we define as a g of x, so that plays the role of a gradient. So when we look at the equations, we can interpret this as a learning rate, which we are dealing with, as learning rate. Which we call gamma of k. And g of x is actually our gradient, which is now calculated at the point x of k. So the way we can now relate this to what we have done is that this parameter alpha of k is nothing but our learning rate. And we have a recipe for evaluating the learning rate, which now involves the full calculation of the Hessian matrix. And you see clearly that this is something we want to avoid. So in our case, H is equal to Hessian matrix, which is the same as the second derivative, which is equal to d second derivative with respect to the parameters beta, the unknown parameters. And if you have hundreds of thousands of these parameters, or even millions, this is something you want to avoid. However, the reason why I want to emphasize this is that if you look at this equation here, this is the equation which is going to be used when we now are going to find approximations to the learning rate. So this is our learning rate. And these different methods like ADA-GRAD, root mean square propagation, and ADAM, they try to combine features of this equation here in order to bake in some information about the gradients. So instead of calculating the full Hessian matrix, you're going to make approximations here, and then different ways of doing that. And we have methods like ADA-GRAD, which computes this with a cheaper recipe for updating with the gradient information. And then we have methods like root mean square propagation, which is a modification of ADA-GRAD. And finally, we have the adaptive gradient, which combines momentum with an adaptive gradient here, or an adaptive learning rate, sorry. So what we're going to do now is actually to go back to the Jupyter Notebook, and we are going to look at the different types of implementations of these methods. So just to quickly remind you, this was meant as a stepping stone in order to motivate the approximations to this learning rate, using now the methods to update the learning rate with either ADA grad, or root mean square propagation, and ADAM. So when you're running calculations with, let's say, neural networks, many people tend to test several methods for updating the learning rate, and also several methods for calculating the gradients. And in some cases, it happens that standard gradient descent with a fixed learning rate does the best job. A priori, you don't know. However, stochastic gradient descent combined with ADA grad, root mean square propagation, or ADAM, is normally what does the best job for us. And it's also the method which saves a lot of CPU cycles and allows a efficient and expedient calculation of gradients. Sorry. So let's go back to the Jupyter Notebook and try to wrap up this discussion by looking at the ways we can implement these methods. So we went through the momentum-based methods, and we looked at second moments of the methods. So this adaptive, this ADA, or this root mean square propagation, for instance, what that one actually does is that it combines some kind of gradient descent with an updated learning rate and some kind of momentum. And this actually includes the, so let me see. Yeah, there's a question here. Go ahead, Damiano.
Oh, thank you so much. So I was wondering whether with this last method that we saw, since there is a dependence of alpha k on the Hessian matrix, we can actually have a difference in approaching the maxima, the local maximum, the local minima.
Yeah, no, that's correct. That's correct what you're saying actually. So what I showed you, the steepest descent, is a method which is pretty easy to implement. But normally what you would do is actually to use something which is called a conjugate gradient descent. And in that way, you ensure that the vectors which you have are really orthogonal to each other. In our case, we simply assume that we had reached the solution so that r of k plus 1 was equal to 0. If you then want to include the requirement that these different vectors are orthogonal to each other, then you enter the field of conjugate gradient descent. Did that help? Is that?
Well, it's very interesting, so thank you. But I was wondering exactly regarding the positive definedness, if you wish, of the Hessian, or the negative definedness. I mean, when you approach the maximum or the minimum, if there is actually a difference in this case, maybe.
Oh yeah. So let me see if I understand correctly your question. So one thing is if your matrix A is positive definite, then if that is the case, then you have a convex optimization problem. That's okay, right?
Yes.
And then if also the matrix is positive definite, you can show that one, you will converge to the exact solution irrespective of starting point x is 0. And two, the minimum is a global minimum. So these are statements which I'm not proving, but which you can actually find in textbooks on convex optimization problems. So these are requirements on the problem which ensure that you actually have a true global minimum. But in general, you don't know whether your function, the cost function, leads to a second derivative which is leads to a convex problem, or whether your Hessian matrix is positive definite. In general, you don't know that. So there's also another thing which is important here, and that is that when you're dealing with the neural networks, you're also going to calculate gradients using these methods, but you don't want the gradients to vanish as a function of a hidden layer. So in neural networks, you will have hidden layers. In the cases we've been looking at here, we are driving the gradients to 0 as a convergence criterion, because then we found the root of the equation we want to find the root of. In our case, is the gradient we want to drive to 0. But when you do a neural network, you are training a network. And if the gradients in a hidden layer go to 0, then the training stops. So what you are going to do in a neural network is that you actually don't want the gradient in the given hidden layers to disappear, but what you want is that your cost function has a gradient which goes towards 0. So there are some delicate issues here. I don't know if this answered your questions.
Yeah, it gave the hint. So thank you.
Yeah. So these are things which actually I have a link to a textbook by Van den Berg, which is in the slides here, which is a textbook which is an excellent read on convex optimization problems. So what I wanted to show you is more the recipes for dealing with this Adam and other methods. And you can also, if you look into the textbook of Goodfellow, Benjo, and Coville in chapter 8, you will find the detailed discussions of these algorithms. But what I've done here at the end, and this is actually another topic which I may touch upon next time, is about automatic differentiation and autodiff. So we won't be fully done with this topic today, but I wanted to show you the algorithms at the end here. And then I'm going to bring back this discussion of automatic differentiation at a later stage, because that is a tool which you will find invaluable. So in this case, I'm just doing, there are different types of examples here. So there's an example of a stochastic gradient descent, or first plane gradient descent with a momentum. And I'm also using this automatic differentiation here. So that I actually calculate derivatives without finding the analytical expressions. So I invite you to take a look at automatic differentiation. I'm going to discuss this next week a little bit, because I see we're getting close to the end. But if you look at the stochastic gradient descent, there's an example here where we include this momentum. And this is just a plain one. And then here you have with momentum. And if you print out the derivatives as a function of this momentum gradient, stochastic gradient descent, as it's implemented here. So when we do the momentum, we have this new change equal to the previous gradients times delta momentum, which becomes a parameter, which I put to 0.3 here. Then you can add AdaGrad. So AdaGrad is a way by which I calculate the gradients, but now with the following recipe. So what I have is first the calculation of the gradient for a given batch, which is this function you see here. So I calculate the gradient. Then what I'm doing next is I'm setting up a recipe where I calculate a function here, which is the sum of the gradient squared. And so that is a kind of reminiscent of this kind of RK, this residual which we looked at. It's not exactly the same. And then I have the gradient multiplied with the learning rate, the original one. But then I scale the learning rate now with a parameter delta, which is meant to avoid possible divisions by 0. And then I multiply this with the square root of this gradient square. So what I'm principally doing here is to have the original gradient multiplied with the original learning rate and divided by the square root of the gradient squared. And that defines my update. So this is the adaptive gradient, AdaGrad. So it's an example of how you can implement it. This is one of the possible methods. So what you're doing now is simply to instead of having a scheduler like an exponential decay of the learning rate or a linear decay, as we discussed in the previous lecture, you would now have a learning rate which is informed by the value of the gradient. So this is one possible way of doing that, and this is a very popular method. And when you run it, you can now see that you have the results from the own inversion. And here you see now with a given learning rate, which is 0.01, and I do 50 epochs. In my case here, I have a function which is a second order polynomial, and I have 1,000 data points. And you see now that with the number of iterations, without having a convergence criterion, which you could implement in order to make a more efficient code, I'm now getting results which are pretty spot on the exact result. And you will also see, if you count the number of iterations here, or look at the value of the gradients, you will actually see that this brings the gradients to zero at a much quicker pace than just a standard stochastic gradient descent. So if you do a stochastic gradient descent, like the one which we have here, so this is a standard stochastic gradient descent with a learning rate, which is now turned in an adaptive way by having this parameter t0, the initial one, or just an initial value here, and then divided by t+1. If you do that, you will see now that you get a value which is not exactly equal to the one you started with. So in this particular case, you actually get a much better result. And you will also see that when you look at the number of iterations, you would then have a result which is actually requires less iterations in order to get gradients which are zero. Then we have root mean square propagation. And for the root mean square propagation, we are actually baking in some kind of knowledge about the previous iteration. So again, we calculate the gradients. We have now an accumulated gradient, but an accumulated gradient which is now scaled with the previous results. So we have a parameter rho, which I put to 0.99. So this becomes a parameter in the calculation of the gradients. You may be disappointed because there are so many parameters which pop up. And this is a parameter you can play around with. We have the same delta here to avoid possible divisions by zero. But now we scale this term here with the previous gradient. And then we have this term which is called gradient squared, as we had with ADA grad. So the difference between root mean square propagation and ADA grad is simply that we now have information about the previous result. And then the second term here, the update, is the same as we had with ADA grad. And this is also a method for the same function now, which, and you will see that this is also a method which gives you results which are pretty close to the exact ones. And finally, ADAM is actually root mean square propagation in a way with a momentum approach baked in. But then you would have additional parameters. So you get this parameter beta 1 and beta 2 here, which are normally tuned to these values which you see here. So you would calculate a first moment where you have information about the previous gradients, but in a linear way. And then you have the second moment now, which contains the gradient squared. And then you have the first term, which now scales the result in terms of just the gradient. And then you have the second term, which scales the result in terms of the second gradient. And then the update is actually given by the first term divided by the square root of the second term here. So this is a kind of root mean square propagation with an adaptive, no, not with adaptive, with a kind of momentum baked in. And this paper, which you can see, if you look up this paper here, this is a paper which was published in 2014, and it has more than 130,000 citations nowadays. And this is a method which is normally the one which is used by most practitioners. And as you can see, for this simple function, this second order polynomial, we are getting results which are basically almost spot on the results from the own inversion. So what people would, as a summary, what people would normally do is to use stochastic gradient descent to evaluate the gradients and to implement either adaptive gradient, which normally works pretty well if your function is convex and you know that the function is convex. Or if you don't know whether the function is convex or not, or whether you have many local minima, people would typically use root mean square propagation or ADAM. And ADAM seems to be the favored method in the literature. So in the first project, you're first going to do a standard linear regression. You're going to do a ridge regression and so on. But then with matrix inversion, but then we are going to replace that, the linear algebra problem with matrix inversion. We are going to replace the calculation of the gradients then, and the recipe for finding the updated parameters beta. We're going to change that with the calculation of gradients using these different methods we have discussed till now. So next week, We are going to start with the neural networks, but I wanted to say something which I haven't covered yet. I wanted to say something about what you will find here in the slides about automatic differentiation, because that's a tool which is going to make life much, much easier. So automatic differentiation is a very important algorithm in machine learning. And we are going to discuss that a little bit before we jump into the calculations of neural networks and the setup of the algorithm for calculating properly neural networks. And that would then define the second project. Okay, I'm going to stop here. I went a little bit over time,